Hello everyone. Hi everyone. Welcome to week 12 live session of NPTEL's Semiconductor Introduction to Semiconductor Devices course. I am Om Maheshwari and today we will solve some questions that will help you with your assignment as well as your exams. So this is the last session of this course. After this, we will take one more summary session. So let us start with a quick recap of the lecture slides for this week. So basically we talk about uh, radiative absorption, emission, could be spontaneous emission or simulated emission. So in radiative absorption, like light energy is absorbed by the holes or uh, by the electrons in the valence band, which then gain energy, take the energy from from the photons to go to the excited state in the conduction band. This is absorption, and then these excited electrons can come down back to the valence band. So that if they emit the light in energy in form of light, it would be called as emission. So it could be spontaneous emission or stimulated emission. So in spontaneous emissions, the photons are emitted at a random instant, whereas in simulated emission, the second photon that is emitted has the same phase and frequency as the incident photon. So the photon which came as in the emitted photons has same phase and same frequency which are emitted. So So this is the relation between spontaneous and simulated emission. Mm, okay, so luminescence means the emission of light energy. So the emissions can be non-radiative or radiative. So radiative ones are luminescent. So in non-radiative decay, the electron loses energy to the lattice in form of phonons. In radiative, we get photons as output, which is so these radiative emissions are used in LEDs or lasers. So there are two types of luminescence, electroluminescence and photoluminescence. So in photoluminescence, the re-emission of light after absorbing a photon of high energy. So when a photon comes, the electron gets excited and then comes down back to valence band, then the luminescence called photoluminescence. Whereas electroluminescence, the emission of photons due by supplying current. So electrons are excited through by giving them some electrical energy. And when those electrons lose energy and come back to the ground state, they give photons. This is what is used in LEDs. So we have various different kinds of light sources throughout our history. So it shows fluorescent lamps, incandescent filter, yellow filtered, red, different colored bulbs, and then LEDs, the red, green, orange, yellow, all have different materials. So the tuning of band gap of materials is very important because the emitted energy depends on um, depends on the band gap. So the photon energy which is emitted, this corresponds to the light wavelength. So the color of the light depends on the band gap of the material. So this band gap. So for example, gallium arsenide and gallium phosphate So by tuning the mole fraction, we can tune the band gap to stay in the uh, direct band gap region for direct emissions. And right, so so there can be different substrates for optoelectronics. So there can be different substrates as we were talking about. So these different substrates can be silicon or germanium, which are like very extensively used currently in the CMOS technology, and they are well developed to large wafer sizes. Whereas gallium arsenide are compared relatively expensive but affordable, and around 12 centimeters of wafer size is available. Indium phosphate and 10 centimeters, and the rest are like very expensive and available only in few square centimeters. So why this substrate is important? Because the material that you are using on the top, uh, if there is a large lattice mismatch between that and the substrate, there could be like due to this lattice mismatch, there can be traps or defects due to different lattice constant of the substrate material and the top material. So because if lattice constant is different, there will be strain, and if the lattice mismatch is very high, that it will become unstrained, and these defects would come into the picture. And we don't want these defects. They create different levels in between AC and EV, and which will disturb our uh, electron emission. So instead of coming directly from conduction band to valence band with the EG of energy, it will transmit to these trap states and may not emit the photons. So we need to have similar lattice matching in the substrate and the top layer. So this graph just shows how the band gap energy and lattice constant are varying, and the wavelength also. So for example, if you have an INP substrate and you want but to select the top layer for a wavelength of around this 1.5 micrometer, then the materials nearby in this region are um, that you need to select so that to have minimum lattice mismatch, and that could be some compounds of gallium, GaAs and IN, and GaAs and SB. Those are the two nearby this red point, right? So LED, we have been talking about LED, and uh, that is just light emitting diode. And so we pump electrons or holes on the different sides which emit light. So this is the quantum efficiency. Mm, Uh, this is the for rate of radiative recombination, rate of non-radiative recombination, total rate. So efficiency is um, radiative recombination by total rate, which is tau by tau r. This is the internal quantum efficiency. And this is the external quantum efficiency. Number of photons escaping the semiconductor by number of photons generated. So you generated photons, but some get refracted. So how many are actually emitted? That is the number of photons escaping the semiconductor divided by total number of photons generated. So this is the typical LED spectrum, intensity versus energy. We want it to be that very concentrated. to have a proper, because if energy is varying too much, it's like very varied wavelengths and intensity will be less. So, and this is how this relation between delta E and delta L is given. So delta E is 1.8 kT, delta L is 1.8 kT lambda square by hc. So mainly we prefer to have double heterostructure. So in double heterostructure, we have, so this gallium arsenide is the light emitting material, right? So the electrons and holes can be will be trapped in this double heterostructure because here the band gap is smaller, here band gaps are larger. So electrons will come from here and holes will come from here and they will get trapped. And photons emitted will also be restricted to this region only. So this is has confinement of both photons and electrons in the double heterostructure. That's why we prefer these kind of structures. That means we will have like restricted um, light and better controls. Okay, so I think we can now go to the questions. So let's see the questions now. So in this week, basically we are talking about LEDs, illumination efficiency, heterostructure, etc. So this is the first question. Which of the following can increase the light emission efficiency in a semiconductor material? Please take a moment to answer this, then we'll solve it. Okay, so the question is, which of the following can increase the light emission efficiency in a semiconductor material? A. Increasing the radiative recombination rate related to non-radiative recombination rate. B. Increasing the non-radiative recombination rate related to radiative recombination rate. C. Increasing the non-radiative lifetime related to radiative lifetime. D. Decreasing the radiative recombination rate related to non-radiative recombination rate. So we know the efficiency we have just seen is RR by R. And this R is RR plus R and R. So we need to increase this compared to this. So correct option is option 1, increasing the radiative recombination rate related to the non-radiative recombination rate. So RR should increase, RNR should decrease. Then the efficiency would increase. Okay, let's see the next one. Try to solve this. All right, so let's see this question. I hope you have solved it. The question is given the two statements on photoluminescence and electroluminescence. Statement 1, photoluminescence is the phenomenon of the emission of light after absorbing a photon of higher energy. Statement 2, electroluminescence is the phenomena of photon emission that supplies current to the semiconductor. You have to choose the correct option. Which of these are correct? So we have seen this in the lecture notes. In photoluminescence, you have some photon first striking the semiconductor, where electron goes at top and which is later emitted. This is photoluminescence. In electroluminescence, you supply some form of electrical energy so that this electron goes from valence band to conduction band and then later gives energy in forms of light. This is electroluminescence. So both statement 1 and statement 2 are correct. Yeah, I hope you all got the same answer. Let us see the next question. Please try to solve this one. It's a very easy question. Okay, so let's see this. I hope you have solved it already. It's a very simple question. So we just saw that quantum efficiency is RR upon R. So RR is delta n by tau R. R is delta n by tau. R is sum of RR plus R and R. So eta will become then tau by tau R. The question says determine the internal quantum efficiency generated within a device when it has radiative recombination lifetime of 10 nanoseconds. So tau R is 80 nanoseconds and total carrier recombination lifetime of 40 nanoseconds. So tau is 40 nanoseconds. So eta is 40 by 80, which is 0.5. Just 50%. Is option B. I hope you have all got the same answer. So let us take the next one. Please read this question and attempt this. We'll solve it after a few minutes then. All right, so let's see this question. The semiconductor alloy GA AS 1 minus X P X has a band gap that varies approximately linearly with composition. For GAP, the indirect band gap is 2.27 electron volt and the direct band gap is 2.78 electron volt. The band gap of the alloy semiconductor GA AS 1 minus X PX varies approximately linearly with composition and is a direct band gap for between 0 x between 0 and 0.45. Calculate the output wavelength of GA AS 1 minus X PX material for mole fraction of 0.45. Okay, so we have to find what is the wavelength for the material GA AS 0.55 P 0.45 for this material from this graph. So you can see here is the x equals to 0.45 line. So this 1.5 is a 1.6, 1.7, 0.8, 1.9, and this cross is nearly at 1.95. So the band gap is 1.95 electron volt. So lambda is 1.24 upon Eg. It is 1.24 upon 1.95. So if you do the calculation, it comes out to be 0.635 micrometer. So this lambda is in micrometer. This is in EV. So this is a 635 nanometer. Option B. So it's a seduced set like a very involved question, but if you solve it, it is very simple. So I hope you all have solved it. So now let us see the next one. Please read this question and attempt to solve it. Then we'll solve it together. Okay, so let us have a look at this question. The question says, consider the theoretical emission spectrum of LED as shown in figure. The full width at half maximum of the emission line is 1.8 QT. Calculate the spectral line width delta L of the LED emitting a wavelength of 400 nanometer, temperature of 300 Kelvin. Okay, so you know that delta lambda is 1.8 kT lambda square by HC, radiant energy. So 1.8 kT will be 1.8 into 0.026 electron volt. Lambda is 400, so in micrometer 3.4 square. Divided by 1.24 in electron volts. So if you solve this, you will get 0.00604 micrometer, which is 6.04 nanometer. So answer is this option. So I hope you get all are getting the same answer. Which is 6.05 nanometers. Okay, so let us go to the next one. Please attempt this question, then we will solve it. Okay, so let us see this question. So the question says, consider the bandgap composition graph of compound semiconductors. Referring to the data, which compounds will you suggest to choose to fabricate the lattice matched LED on INP substrate? So we have we have an INP substrate. So INP substrate is this, right, around here, and we want a lattice matched LED. Lattice matched means this lattice constant should be nearby this INP substrate's value. Then only you will have lattice matching, right? Next is the wavelength is given as 1.55 micrometer, which is this already highlighted line. Now we just have to see where these two intersect within this area, and this is this line and this line, right? So this one is GAASIN, and this one is for GAASSB. So these compounds, Mm. so these compounds will give you the desired uh, lattice lattice matched LED with 1.5 micrometer of wavelength. So this should be these two. Okay, let's take the next one. Consider the IV characteristics of various light emitting diodes made up of different materials. Based on this figure, which LED is likely to emit light with longest wavelength? So what is the answer to this question? We know that the threshold voltage of LED proportional to 1 by lambda. So EG is proportional to 1 by lambda. It's proportional to VT. So, so if VT is low, lambda will be highest. So longest wavelength. So VT, lowest VT is of A, right here. So A material will have highest lambda. Answer is A. All right, let's see the next one. Consider the structures for fabricating gallium arsenide laser. Which structure will you prefer and why? We have seen this in the revision. So the answer is structure A, right? Because it has confinement on both the sides. So electrons are also confined and the photons will also be confined to this region. So structure A, as it confines both electrons and photons, being a double heterostructure. Next question. If source A represents an LED and source B represents a laser, which source A or B exhibits higher monochromaticity? Monochromaticity means single color. So a single color will have single wavelength. So among A and B, whichever have less dispersion in wavelength will have monochromaticity. So here we can see this is B, this is A. So delta lambda of B is much less than delta lambda of A. So B must be more monochromatic than A. So the answer is source B exhibits higher monochromaticity due to narrower emission at specific wavelength. Okay, so this is the last question for today. Please attempt it, then we'll solve it. All right, so let's solve this. If the coefficient of simulated emission for a particular transmission is 2 into 10 to the power 19 meter cube per watt per second cube, and the emitted photon is at wavelength 300 nanometer, when the lifetime of the excited state is approximately what? So we know this relation 8 to 1 is 8 pi h nu cube by c cube to b to 1. So, and also tau is 1 by a to 1. So it will be c cube upon 8 pi h nu cube b to 1. C cube by nu cube will be lambda cube upon 8 pi h b to 1. So if we substitute the values, lambda is 300 nanometer, 300 into 10 to the power minus 9 cube divided by 8 pi 6.626 into 10 to the power minus 34 to 2 into 10 to the power 19. If you solve this, you get 81 into 10 to the power minus 9 second, which is around 80 nanoseconds. The answer is option C, 80 nanoseconds. Okay, so this is all for this week's lecture. So if you have any doubts, you can ask them or you can email me. We'll meet again uh, day after tomorrow for the summary session. Thank you for joining. See you in the summary session. Okay, so you have doubt in week 2, question number 5. So let me just open that. So is this the question? Okay, so I'm assuming this is the question. This is week 2, question number 5. So let me just solve it. So in this question, we have been given so n is 1 by t. We have to tell which region is which, 1, 2, and 3. So first I'll draw opposite n versus t. If I take n versus t, it will look something like this, right? So this is the 1, this is 2, this is 3. So in this region, so Ni increases with temperature, something like this is Ni. So in this regions, in region 3, there is partial when there is very less temperature. there is so when we have less temperature, there is small ionization, right? So we have EC, EV is ED. You still need some energy for the donor atoms to donate the electron to EC. So here when temperature is very low, there is partial ionization. So this is partial ionization. After certain temperature, all are ionized. Then you on increasing energy, your ionization will not change. So this is complete ionization. And after certain time, certain more temperature range, your Ni will increase so much that it will be more than Ni will become more than Nd, your doping. So this becomes then again intrinsic. Even though you have doped, but your doping, after you have increased temperature so much that the intrinsic carrier concentration is more than the doping. So the material again behaves, semiconductor again behaves like intrinsic. So here one is intrinsic. This is complete ionization. This is partial ionization. Now complete ionization is extrinsic semiconductor. I hope this is clear. Okay then. Thank you for joining. We'll meet again in the summary session. Thank you.